Welcome to Prerequisites for Calculus video number 2. This video is focusing on function composition and exponential and logarithmic functions. And these are things, again, that you've seen in pre-calculus or before that, and these are just the main parts from chapter 1 that I want to focus on so that we'll be best prepared for calculus. Function composition means that we are composing two functions to create a brand new one. And I realize I use the word in its definition, but to compose just means to create something new. So we're kind of mashing two functions together and creating a new one. So let's take a look. I know this page looks a little confusing, but up here what I have boxed up here in black and starred is what function composition looks like. It looks like f of g of x, or g of f of x. And this is not the only way to write it. Sometimes this is referred to as fog and goff because this little composition notation mark looks like an O. It just kind of is more like a degree symbol but smaller. So f of g of x and g of f of x is how we say that. Our example, we're going to let g of x be this quadratic function, and we'll let f of x be this linear function. And what we want to do first is compose them in two different ways. So what f of g of x looks like here in number 1 is it really looks like f of g of x. We can rewrite it just like that. It equals the same thing. And that's what I prefer because visually it makes more sense. So what we're doing, instead of evaluating our function f at a number, we're not plugging in a number for x. What instead we're doing is plugging in this other function, g of x. So I'm going to rewrite it once more. I'm going to say, hey, this actually equals, take away this equal sign here, and we'll work vertically. So instead of writing g of x, I'm going to write what g of x is. It's x squared plus 3. So that's literally what we're inserting into this function here. So I'm going to insert x squared plus 3 into this f of x function. So instead of x, I'm going to insert x squared plus 3 in place of x. So x squared plus 3. And then after that, we still have a minus 7. So that'll come next, minus 7. And then cleaning up, we'll have x squared minus 4. So in conclusion, those three dots mean therefore f of g of x is x squared minus 4. That is the new function we have created. All right, let's take a look at number 2. We're just going to go the other way. Let's make a little more room here. So we want to find g of f of x, and this one's already written in a nice way visually. So what we're doing is we're saying g of f of x. What is f of x? F of x is x minus 7. And g of x is up here. So I'm plugging in x minus 7 and squaring it and then adding 3. So we'll move that up here because this will take some room. So we're taking x minus 7 and squaring it and then adding 3 because we're plugging this in to the g of x function. And this function says square whatever we plug in and then add 3. So we're going to square x minus 7. Remember that means x minus 7 times x minus 7. And then we'll add 3. When we FOIL it or just multiply, we'll get x squared minus 7x minus 7x plus 49 and then plus 3. So we'll end up with x squared minus 14x plus 52. So in conclusion, we are left with g of f of x is x squared minus 14x plus 52. So we have composed those two functions and gotten something new because of the order of composition was different. Okay, number 3, the very last one that we're going to take a look at, is we want to find f of g of negative 1. Now, there's a couple different ways to do this. What we can do is actually realize, hey, we created a function. We created the function f of g of x already. And so all we need to do is plug in negative 1 into that function. So let's do that. We know that the function f of g of x, we found it in part 1, is x squared minus 4. and we want to plug in -1 to that function. So we're going to plug -1 in for x. When we square it, we'll get 1 minus 4, which is -3. There is an alternate way of doing this, so I'm going to show that way next. All right, the alternate way of doing this is working from the inside out. So what we can first do is work on the inside. We'll actually find g of -1. So g of -1 means we are going to look at the g of x function and plug in -1. So let's do that first. So it's -1 squared, and then we'll add 3. So that gives us 1 plus 3, gives us 4. So what we're really doing, working straight across, is we're really finding f of 4. Why is that? We found that g of -1, this whole thing in here, is 4. Therefore, we're replacing g of -1 with what it equals, 4. So now we need to find f of 4. How do we do that? Well, we look at our f function and we plug in 4. So we'll get 4 minus 7, and that equals -3, the same value we got earlier. So there's two different ways of doing those function compositions. The moral of the story is composing functions will create a new function. Well, that got a little messed up there. Okay, so composing functions, when we plug in x, you'll get something out that has x in it, just like in numbers 1 and 2. Whoops, we got a new function there. It's got a little messed up. There we go. And then if you plug in a number, you'll get a number out. And I showed two different ways for doing number 3. The next main idea in this video is going to be exponential functions. So in general, an exponential function is when the exponent is the variable. So this is the general form of an exponential function. And I believe in Algebra 1, it might be Algebra 2, you learned about exponential growth and decay. And that generally was used with word problems for population, because population doesn't increase on a line, like in a linear way. It increases exponentially as more and more people reproduce, right? And our population increases. We also saw probably exponential decay with half-life of a radioactive substance. So those are common examples that you probably saw in Algebra 1 or 2. But we're not going to get super into the growth and decay. I just want to do a quick recap. So in general, this is what an exponential function looks like. F of x equals a times b to the x. And the a is considered the initial value. And then b, the value that's actually being raised to the x power. B is considered either the growth rate or the decay rate, depending on how big b is. So if b is greater than 1, then we're growing. And if b is between 0 and 1, we're actually decaying. If b is 1, it's not an exponential function because 1 to the anything is still just 1. So that is in general what an exponential function is. I wouldn't worry too much about this part up here. I'm just defining it. Let's take a look at some examples. These are 3 examples of exponential functions. This first one is h of t 2.7 times 0.01 to the t. All right, so this 2.7 is our initial value, and the 0.01 is our decay rate because it's between 0 and 1. The second one, f of x, is 2 to the x. A is actually 1 here. We just don't see it. We wouldn't write 1 times 2 to the x. So this is a growth function because 2 is greater than 1. And then g of x equals e to the x. We'll talk about that in just a second. E is just a number as well. It's just a little bit bigger than 2. All right, let's take a look at finding h of 0 here off to the right. So if we're looking for h of 0, that means basically what is the initial value, right? What is our value at time 0? So that means we want to plug in 0 for t. When we do that, and we evaluate what this is, remember anything to the 0 power is 1. So this is 2.7 times 1, which is 2.7. That is why this value of a here is called the initial value. Because if you were to plug in 0 for x, meaning at time 0, what's happening initially at the beginning, this will end up being 1, and you're left with just whatever a is. Let's take a look at finding f of 0. We mentioned that in the function f, a is 1. So let's see that we get a 1 out here. Well, if we plug in 0, we'll have 2 to the 0, which is 1. Again, that exponential rule there. Anything to the 0 power is 1. And then if we plugged in 0 here, we would also get 1 out. But I want to talk quickly about what E is. Should have been exposed to E in pre-calculus. E is about 2.718, and it actually goes on forever. It is an irrational number. And I would say that out of all the infinite irrational numbers that exist, pi and E are two of the most special and well-known. Pi is much more well-known, but E is important, and there's plenty of reasons why it's important. I'm not going to get into a lot of them, but we'll see later in calculus this year that this will actually be its own derivative. So that's why E is such a cool number. So it's irrational. It's closer to 3 than 2, but if you had to make an approximation, it's 2.7. And if you look on your calculator, you will see above the on the division key, if you have a TI-84, that there's an E option up there. The last main topic I want to hit is logarithmic functions, and we are going to focus both on those with a base 10 and those with base E. So we'll look at this one second. F of x equals log base 10 of x. I say base 10 and I don't have to. It's one of those things in math where you don't have to write. Just like if you wrote x, we know that you mean 1x. You don't have to put the 1 in front. So with log of x, there's secretly a little 10 down here that we don't see. We assume base 10. This is mainly because we're in the base 10 number system. All right, so let's plug in a couple points, and I drew this little thought bubble above here to help us with how to think about logs. So I can only plug in certain numbers, and you'll see why. So let's first plug in. Let's plug in, I'm going to put it in this table here, table of values. Let's plug in the number 1. So if we plug in 1, I want to find f of 1. So this is saying log, and there is a little base 10 down here. Again, you don't need to write it, but I'm going to. All right, so let's look at just this little part right here for now. Just going to look at this part and think about it in our thought bubble. So we're asking ourselves, the base is 10. 10 to the what is going to give me a 1. That's what this is going to be equal to right here. 10 to the what gives us a 1 output? Well, 0. 0. So when we input a 1 here, our output is 0. Let's try plugging in a different number. Let's plug in 10 next. So that means, okay, I need to plug in 10 here. It's just a function. So this is log of 10. Again, there's a little 10 down here. If you want to write it, you can. I wrote it in this example. You can write it here. So let's go to our thought bubble again. And we're thinking, all right, 10, that's our base 10. 10 to the what gives us this output of 10? This guy. Well, 10 to the first gives us 10. 1. So when we plug in 10, we output a 1. Let's try 2 more. Let's try plugging in 100. So I want to know, what is log of 100? Again, I'm plugging this all into my original function here. All right, what is log of 100? That means we have a base of 10. So we're thinking 10, our base here, this is called a base, 10 to the what will give us 100. Well, 10 squared will give us 100, so the answer is 2. So that means when we plugged in 100 into our function, our output was 2. I'm going to have you try 2 on your own. I want you to try on your own plugging in 1,000 into our function, and then plugging in 0.1. Pause, try that, and then click to see what the answers are. Okay, you can see what the two solutions are here. Plugging in 1,000 still follows our pattern. We'll get 3 if you saw the pattern there. So log of 1,000 is 3. And then log of 0.01 or 1/10. 10 to the what will give us 1/10, and that's -1 because of the properties of negative exponents. Okay, just like log of x was base 10 without seeing it written, the natural log of x is base e. This is ln, so sometimes you'll hear it referred to, and I'll refer to it as ln of x, or I might refer to it, or it might be referred to in general as the natural log of x. Why is it ln if it's natural log? Because it's French where the adjective comes second, log natural. All right, so this is base e. So if you want, you can put a tiny little e down here. I mentioned e on the previous slide, and e is about 2.7. It's an irrational number, and it's just important and kind of cool. So it is the base in natural logs. And so this is the exact same thought process, except besides a base of 10, we're going to do a base of e. So there's not as many that we can just know off the top of our head because it's an irrational number, and 10 is so much easier to think about, raising to a power. So let's just do a couple here. Let's try g of 1. So g of 1 would mean what's the natural log of 1? So our thought process is going to be, since it's base e, e to the what will give us 1. Again, because I'm trying to figure out what is the natural log of 1, the base is e, and logarithms are exponents, so I'm looking for what is the exponent that if I raise e to it, I'll get a 1 out. Well, I know that if I raise any number to the 0 power, I'll get a 1. So the natural log of 1 is 0. So when we plugged in 1 to our function, we got an output of 0 because of the way logarithms work. All right, next let's try plugging in e. So I want to find what is the natural log of e. So we're thinking e to the what will output e. Well, e to the first power will output itself. So if we plug in e, we'll get out 1. These are really the only two that we can really just know off the top of our heads. So really an important thing that you do need to write down is that the natural log of e is 1. This is an important idea in calculus, and we'll see it quite a bit. Okay, that's the end of the second video for the prerequisites for calculus. I hope you enjoyed that and got a quick refresher on a lot of these pretty big mathematical concepts.